Good morning, everyone, and welcome to today's presentation. My name is Associate Professor Yasser M. Madany. I'm a senior member of IEEE and a senior member of URSI. Today, I'm excited to talk to you about the Discrete Time Fourier Transform and its various applications within digital signal processing. Over the course of this presentation, we will explore the fundamentals of DTFT, its significance, and how it is utilized in real-world scenarios. Let's get started. The Discrete Fourier Transform, or DFT, is a fundamental tool in the world of digital signal processing. It allows us to transform a sequence of values into components of different frequencies, which can be incredibly useful in a variety of fields, from audio signal analysis to image processing. The DFT is a practical and accessible concept once broken down into its basic elements. Understanding this transformation helps us analyze signals more effectively, revealing their underlying frequency content. This capability is essential for many modern applications, making the DFT a cornerstone in the field of digital signals. Let's take a moment to look at the background behind this topic. Understanding the background is crucial because it sets the stage for everything that follows. It helps us grasp why this issue is important and how it has developed over time. By exploring the background, we can see the context in which these challenges or opportunities exist. This foundation allows us to better appreciate the significance of the solutions or strategies we'll discuss later. Overall, having a clear background helps us connect the dots and see the bigger picture within the overall theme of this presentation. So, what is the DFT? The Discrete Fourier Transform, or DFT, is a powerful mathematical tool that helps us convert data from the spatial or time domain into the frequency domain. Essentially, it takes a finite sequence of samples, think of these as snapshots taken at regular intervals, and breaks them down into a sum of sinusoids, each with different frequencies. This process allows us to see the underlying frequency components that make up our original signal. The key benefit here is that the DFT provides a frequency domain representation of a signal, which can often be more insightful than just looking at it in the time or spatial domain. By understanding the different frequencies present, we can perform various tasks, like filtering out noise, reconstructing signals, or analyzing their characteristics more deeply. This concept is central to many areas of signal processing and ties directly into the overall theme of analyzing and manipulating signals through their frequency content. Let's take a moment to explore the background behind this topic. Understanding the context is crucial because it sets the stage for everything that follows. Here, we'll look at the key factors that have shaped the current landscape. These points are fundamental in grasping why this issue is so important today. As we go through, I'll connect these background elements to the overall theme of the presentation, showing how they inform our approach and solutions. So, keep this background in mind, as it provides the foundation for everything we're about to discuss. Let's take a moment to look at the background behind our topic. Understanding the background is crucial because it sets the context for everything we're about to discuss. It helps us see how the current situation evolved and highlights why this issue is important. By exploring the background, we can better appreciate the challenges and opportunities that lie ahead. This foundation connects directly to the overall theme of the presentation, as it helps us understand the bigger picture and the relevance of the solutions we'll explore later. So, keep in mind that this background isn't just historical information, it's the starting point for our entire conversation. The Discrete Fourier Transform, or DFT, plays a crucial role in modern technology because it allows us to analyze and process digital signals efficiently. When we think about telecommunications, the DFT is fundamental for modulating and demodulating signals, which means it helps ensure that data is transmitted and received accurately across various channels. Moving into audio processing, the DFT enables us to perform noise reduction, compression, and enhancement by identifying and manipulating specific frequency components within audio signals. This is what helps improve sound quality in many devices. Additionally, in imaging technologies, DFT is vital for tasks like image filtering and reconstruction. This is especially important in medical imaging, such as MRI and CT scans, where clear, accurate images are essential for diagnosis. Overall, DFT's ability to analyze signals in the frequency domain makes it an indispensable tool across multiple fields, connecting directly to the overarching theme of how mathematical transforms impact our everyday technology. Let's take a closer look at the basic concepts of the Fourier transform. At its core, the Fourier transform is a mathematical operation that takes a function of time or space and converts it into a function of frequency. This means it helps us understand what frequencies make up a signal. The key idea here is that any complex signal, no matter how complicated, can be broken down into a sum of simple sine and cosine waves. Each of these waves has its own specific frequency, amplitude, and phase. By identifying these components, the Fourier transform gives us valuable insight into the behavior of the original signal. Now, when dealing with digital signals or discrete data sets, we use a specific version called the Discrete Fourier Transform, or DFT. The DFT is essentially the same idea, but tailored for digital applications. This concept is fundamental because it underpins so much of how we analyze signals in various fields, from communications to image processing. Let's take a moment to explore the background behind this topic. Understanding the context is crucial because it helps us see why these issues matter and how they fit into the bigger picture. When we look at the background, we're really setting the stage for the rest of the presentation. It highlights the key factors and historical developments that have shaped the current situation. By grasping these foundational points, we can better appreciate the challenges and opportunities ahead. So, as we move forward, keep in mind that this background information is the lens through which we'll interpret the rest of the content. It's all about connecting the dots and building a solid understanding of why this topic is so important today. Let's take a moment to look at the background of our topic. Understanding the context is crucial because it helps us see how everything started and why it matters today. The background provides the foundation for the ideas we're exploring, highlighting the key developments and the environment in which these changes occurred. By grasping this background, we can better appreciate the relevance of the solutions and strategies we'll discuss later. It connects directly to our overall theme of growth and innovation, showing us where we've come from and guiding us toward where we're headed next. Let's take a moment to delve into the background behind this topic. Understanding the context is essential because it sets the foundation for everything we'll discuss moving forward. When we talk about background, we're really looking at the history, the key factors, and the environment that shaped the current situation. It's important to recognize how these elements influence the decisions we make today, as well as the challenges we face. By connecting these points to the overall theme of the presentation, we can see how past developments inform current strategies and future opportunities. This background helps us appreciate the complexity and the significance of the topic at hand, giving us a clearer perspective as we move into more detailed insights. Let's take a moment to explore the background behind this topic. Understanding the context is crucial because it gives us insight into how we arrived here and why these issues matter. As we go through, I'll highlight some key points that connect back to the overall theme of our presentation. This background sets the stage for the solutions and strategies we'll discuss later, so keeping this in mind helps us see the bigger picture. It's about understanding the foundation so we can build effectively on it. Let's start by discussing the Fourier series representation of discrete time periodic signals. This is a fundamental concept because it allows us to express any periodic signal as a sum of complex exponentials, which simplifies analysis and processing. Understanding this helps us see how signals behave in the frequency domain. Next, we'll look at the properties of discrete time Fourier series. These properties, such as linearity, symmetry, and convergence, give us insight into how the Fourier series behaves and how we can manipulate or interpret these signals effectively, especially in the context of digital systems. Moving on, the discrete time Fourier transform, or DTFT, is an extension that allows us to analyze aperiodic signals or non-periodic components of signals in the frequency domain. It provides a continuous spectrum, which is very useful for understanding the frequency content of signals that aren't strictly periodic. Then, we explore the Fourier transforms of discrete time periodic signals. This is interesting because periodic signals in the time domain correspond to discrete spectra in the frequency domain, often represented as impulses. Recognizing this duality is key to understanding the relationship between time and frequency representations. Following that, we consider the properties of the discrete time Fourier transform. These include properties like duality, shift, and scaling, which help us manipulate and interpret signals more effectively, especially when designing filters or analyzing system behavior. Speaking of duality, it's a fascinating concept where the Fourier transform exhibits a symmetrical relationship between the time and frequency domains. When you transform a signal, certain properties mirror each other, which simplifies many analysis tasks. Finally, we outline the DTFT in this section. The DTFT bridges the gap between the Fourier series and the Z-transform, providing a comprehensive tool for analyzing discrete time signals, whether they are periodic or aperiodic, in a unified framework. Throughout this slide, the overall theme is understanding how signals can be represented and analyzed in the frequency domain. These tools and properties are foundational for signal processing, communications, and many other applications in engineering. Let's start by looking at the introduction. This slide sets the stage for everything we're going to cover. It's about understanding the core ideas and framing our discussion. I'll explain the key points thoroughly, but in a conversational way so it feels natural. The most important concepts here are the foundational principles that will guide us throughout the presentation. As we go through, I want you to see how these points connect to the overall theme, helping us understand the bigger picture. This introduction is really about establishing a clear understanding and setting a solid context for everything that follows. Let's take a closer look at the analysis and synthesis equations. These are fundamental tools in signal processing that allow us to understand and manipulate signals more effectively. The analysis equation helps us break down a complex periodic signal into its basic components, while the synthesis equation enables us to reconstruct the original signal from these components. Now, connecting this to the Fourier series representation of discrete time periodic signals, it's really about how we express these signals as a sum of simple sinusoidal functions. This representation is powerful because it provides a clear frequency domain perspective, which is essential for analyzing signals in various applications. By understanding these equations and their relationship to Fourier series, we gain a deeper insight into how complex signals can be decomposed and reconstructed. This not only enhances our analytical capabilities, but also underpins many practical signal processing techniques we use today. Now, let's look at an example to illustrate the solution. Here, we have example 1. This example helps us understand how the concepts we've discussed can be applied in a practical situation. By walking through this example, we can see the key points in action and better grasp their real-world relevance. Remember, the goal is to connect these details to the overall theme of the presentation, showing how the solution can be effectively implemented in similar scenarios. Now, continuing with our solution, let's delve deeper into some of the key points. First, it's important to understand that this approach is designed to address the specific challenges we identified earlier in the presentation. By focusing on these targeted strategies, we can ensure a more effective implementation. One of the most critical concepts here is adaptability. We need to be flexible enough to modify our methods as we gather more data and feedback. This dynamic approach allows us to stay aligned with our goals and respond to any unforeseen obstacles. Another essential aspect is collaboration. Success hinges on teamwork and open communication across different departments and stakeholders. When everyone is on the same page, we can leverage diverse perspectives and expertise, ultimately strengthening our solution. Finally, I want to emphasize that this isn't just about implementing a single fix. It's about creating a sustainable, long-term framework that continually evolves and improves. This ties back to our overarching theme of continuous improvement and innovation. By keeping these points in mind, we're setting ourselves up for success and ensuring that our solution truly makes a difference. Let's continue exploring the solutions. On this slide, we'll delve deeper into some key points that are essential for understanding how we can effectively address the challenges discussed earlier. First, it's important to recognize that implementing these solutions requires a comprehensive approach. We need to consider not just the technology itself, but also the people and processes involved. This holistic view ensures that our strategies are sustainable and adaptable. Next, I want to highlight the significance of collaboration. Bringing together various stakeholders, whether it's teams within our organization or external partners, can lead to innovative ideas and more effective implementation. When everyone is working towards a common goal, the solutions become more robust and impactful. Finally, remember that continuous evaluation and improvement are crucial. As we move forward, we should regularly assess the effectiveness of our solutions and be willing to make adjustments. This iterative process helps us stay aligned with our overarching objectives and ensures long-term success. Connecting these points to the overall theme, it's clear that solving complex problems isn't about a one-size-fits-all answer. It's about integrating multiple strategies, fostering collaboration, and maintaining flexibility. That way, we can create resilient solutions that truly make a difference. Let's take a closer look at the properties of the discrete time Fourier series. These properties are fundamental because they help us understand how the Fourier coefficients behave and how they relate to the original signal. First, the periodicity property tells us that the Fourier coefficients repeat every 2 pi, which reflects the periodic nature of these series. Next, symmetry properties, such as conjugate symmetry, give us insight into the real and imaginary parts of the coefficients. This is especially useful when analyzing real-valued signals. Another key point is the linearity property, meaning that if we have a sum of signals, their Fourier coefficients just add up accordingly. This makes analyzing complex signals more manageable. The shift property is also important. It explains how delaying a signal in time affects its Fourier coefficients by a phase shift. Lastly, understanding these properties connects directly to how we analyze and process signals in the frequency domain, helping us to design filters, analyze system responses, and understand signal behaviors more intuitively. These properties are the building blocks that make Fourier analysis such a powerful tool in signal processing. Now, let's take a closer look at the properties of the discrete time Fourier series. These properties are fundamental because they help us understand how the Fourier series behaves and how it relates to the original signal. First, we have linearity, which means that if we have a sum of signals, their Fourier coefficients just add up accordingly. This property makes analyzing complex signals much easier. Next is time shift, which tells us that shifting a signal in time results in a phase shift in its Fourier coefficients. This is crucial when we're dealing with signals that are delayed or shifted. Conjugate symmetry is another key property, indicating that for real-valued signals, the Fourier coefficients have a specific symmetric relationship, which ensures the signal remains real in the time domain. Then we have periodicity, meaning the Fourier coefficients repeat every 2 pi, reflecting the periodic nature of the Fourier series. Lastly, the magnitude and phase of the coefficients tell us about the signal's spectral content, the strength of different frequency components, and their phase relationships. Connecting all this back to our overall theme, these properties not only give us insight into the structure of discrete signals, but also enable us to manipulate and analyze signals effectively in the frequency domain. All right, let's take a closer look at this slide. Here, we're focusing on the solution aspect, specifically through an example. When we talk about solutions, it's really about how we can practically address the challenges we've discussed earlier. And using an example helps make this more tangible and relatable. So, in this case, we're illustrating a specific scenario or approach that demonstrates how the solution can be implemented effectively. The key here is to understand not just the theory, but how it works in real-world situations. This example will help us see the practical application and highlight the most important concepts behind the solution. Ultimately, Connecting these dots reinforces why this approach is valuable and how it fits into the overall strategy we're exploring. Continuing with our solution, I want to emphasize that implementing these strategies is crucial for overcoming the challenges we've discussed. It's not just about having a plan, but about executing it effectively. One key point is the importance of adaptability, being flexible and ready to adjust our approach as circumstances evolve. This ties back to the overall theme of resilience and proactive problem-solving. Another important aspect is collaboration. Working together allows us to leverage diverse perspectives and skills, which ultimately leads to more innovative and sustainable solutions. Remember, no single person or team has all the answers, so fostering open communication is vital. Lastly, consistent monitoring and feedback are essential. We need to regularly review our progress, learn from what's working and what's not, and refine our strategies accordingly. This iterative process helps ensure that our solutions remain relevant and effective over time. So, in summary, these elements, adaptability, collaboration, and continuous improvement, are the key to turning our solutions into lasting success. Let's continue exploring the solution. On this slide, I want to emphasize the key points that build on what we've discussed so far. First, it's important to understand that implementing these strategies requires a clear focus on practical steps. We need to identify the most impactful actions and prioritize them effectively. Another critical aspect is ensuring that our approach is adaptable. The environment and challenges can change, so our solutions must be flexible enough to evolve as needed. This flexibility helps us stay resilient and maintain progress over time. Additionally, collaboration plays a vital role. Engaging different stakeholders and leveraging diverse perspectives can significantly enhance the effectiveness of our solutions. When everyone is aligned and working towards common goals, the results are much more powerful. Finally, I want to highlight the importance of continuous evaluation. Regularly reviewing our progress allows us to make data-driven adjustments and ensure we're on the right track. Connecting these points back to our overall theme, it's clear that thoughtful, adaptable, and collaborative solutions are essential for sustainable success. Now, let's continue exploring the solutions. On this slide, I want to emphasize some key points that build on what we've discussed earlier. First, it's important to recognize that implementing these solutions requires a strategic approach. We need to consider not only the technical aspects, but also the human factors involved. Another critical point is the importance of adaptability. As circumstances change, our solutions should be flexible enough to evolve accordingly. This ensures long-term success rather than just short-term fixes. Additionally, I want to highlight the value of collaboration. No single team or individual can solve these complex challenges alone. By working together and sharing insights, we can develop more robust and innovative solutions. Finally, connecting these ideas to the overall theme, remember that sustainable progress depends on thoughtful planning, continuous improvement, and collective effort. These principles will guide us toward achieving our objectives effectively. Let's take a closer look at the Discrete Time Fourier Transform, or DTFT for short. This is a fundamental concept in signal processing because it allows us to analyze the frequency content of discrete time signals. Essentially, the DTFT transforms a sequence of data points into a continuous spectrum of frequencies, giving us insight into the signal's behavior in the frequency domain. One key point to remember is that, unlike the Fourier transform for continuous signals, the DTFT is specifically designed for sequences that are sampled at discrete time intervals. This makes it incredibly useful for digital signal processing applications. Additionally, the DTFT has some important properties, such as periodicity in the frequency domain, which stems from the discrete nature of the time domain. This periodicity means that the spectrum repeats itself, and understanding this helps us avoid confusion when interpreting the results. Overall, the DTFT bridges the gap between time domain data and frequency domain analysis, which is crucial for designing filters, analyzing signals, and understanding the underlying characteristics of digital systems. It's a cornerstone concept that connects many aspects of digital signal processing, and mastering it provides a solid foundation for further study. Now, let's take a closer look at the Discrete Time Fourier Transform, or DTFT for short. Essentially, this is a powerful tool that helps us analyze the frequency content of signals that are sampled at discrete intervals. Unlike the continuous Fourier transform, the DTFT is specifically designed for signals defined only at set points in time, which is common in digital signal processing. One of the key points here is that the DTFT transforms a discrete time signal into a continuous function of frequency. This allows us to see how different frequency components are present in our signal, even though we're working with samples. It's also important to understand that the DTFT provides a detailed frequency spectrum, which is invaluable when analyzing signals for filtering, compression, or other processing tasks. It acts as a bridge, giving us insight into the signal's behavior in the frequency domain, which complements the time domain view. Connecting this to the overall theme, the DTFT is fundamental because it helps us understand signals in a way that's most useful for digital systems, by examining their spectral content. This understanding is essential for designing effective algorithms and systems in digital communications, audio processing, and many other fields. Today, we're going to delve into the Discrete Time Fourier Transform, or DTFT for short. This is a fundamental concept that helps us analyze discrete signals in the frequency domain. Essentially, the DTFT transforms a sequence of discrete time signals into a continuous spectrum, giving us insight into the different frequency components that make up the signal. One key point to understand is that the DTFT provides a way to understand the frequency content of signals that are sampled in time, which is crucial in digital signal processing. Unlike the Fourier series, which works with periodic signals, the DTFT applies to aperiodic signals and produces a continuous spectrum. This continuous spectrum is particularly important because it allows us to see how energy is distributed across all frequencies, even when working with discrete data. It forms a bridge between the time domain and the frequency domain, enabling us to analyze signals more comprehensively. By understanding the DTFT, we can better grasp how digital systems process signals, filter noise, and perform various forms of analysis. It ties back to our broader theme of understanding signals in both their time and frequency representations, which is essential for effective signal processing and system design. Now, let's look at this third example to see how the solution can be applied effectively. This example really highlights the key points we've been discussing, demonstrating how the concepts come together in a practical way. It's important to note how this approach not only addresses the problem, but also aligns with our overall theme of innovative and effective solutions. By examining this example, we can better understand how to adapt these strategies to our own situations, ensuring we achieve the best possible outcomes. Now, moving on to the continuation of our solution, I want to highlight some additional key points that are crucial for understanding the full picture. First, it's important to recognize that implementing these strategies requires a tailored approach, one that considers the specific context of your organization. Next, collaboration plays a vital role here. Working across departments and with stakeholders ensures that everyone is aligned and moving in the same direction. Another essential aspect is leveraging technology, which can streamline processes and provide valuable insights. But remember, technology alone isn't enough. It needs to be integrated thoughtfully with your human resources and workflows. Finally, I want to emphasize the importance of continuous improvement. Solutions shouldn't be static. They need regular evaluation and adjustment to stay effective and relevant. All these points connect back to our overarching goal, creating sustainable, impactful change that drives long-term success. Let's continue exploring the solution. Here, I want to emphasize the importance of understanding the key points thoroughly, but in a conversational way. It's not just about listing facts, It's about making the information relatable and engaging. I'll highlight the most important concepts because those are what really drive home the message. Connecting these points to the overall theme of our presentation helps reinforce how each part fits into the bigger picture, showing the relevance and impact of what we're discussing. This approach ensures that our audience stays engaged and takes away clear, meaningful insights from this section. Let's dive into the Fourier transforms of discrete time periodic signals. First, it's important to understand that when we analyze periodic signals in discrete time, their Fourier transform provides us with a frequency domain representation that reveals the signal's spectral content. Because the signals are periodic, their Fourier transform consists of discrete spectral lines, often called harmonics. These harmonics occur at integer multiples of a fundamental frequency, which is tied to the period of the signal. This is a key concept because it links the time domain periodicity directly to a discrete set of frequencies in the frequency domain. It's also crucial to recognize that the Fourier series and the discrete time Fourier transform are closely related here. While the Fourier series gives us a sum of harmonics for periodic signals, the Fourier transform extends this idea to analyze how signals behave in the frequency domain more generally. Connecting this to the overall theme, understanding these transforms helps us analyze and process signals efficiently, whether it's filtering, modulation, or other signal processing tasks. It shows how periodic signals, despite their complexity in the time domain, have a predictable and structured spectral representation that we can leverage in many applications. Let's take a closer look at this slide. The Fourier transform of a periodic signal can actually be directly constructed from its Fourier coefficients. This is a fundamental concept because it shows how the frequency components are embedded within these coefficients. When we talk about the Fourier transform, we're essentially translating a signal from the time domain into the frequency domain. The key point here is that, for periodic signals, these Fourier coefficients hold all the information we need. Now, to make sure this relationship holds true, we need to validate the equation by evaluating its inverse transform. By doing this, we confirm that we can go back and forth between the time and frequency representations accurately, which is essential for signal analysis and processing. Overall, this connection between Fourier coefficients and the Fourier transform is central to understanding how we analyze signals in the frequency domain. Now, let's look at an example to illustrate this solution more clearly. On this slide, we're focusing on example 4, which helps us understand how the proposed approach can be applied in real-world scenarios. The key point here is to see how the concepts we've discussed come together in a practical context. By examining this example, we can better grasp the effectiveness and potential of the solution. Remember, connecting these points to the overall theme of the presentation is crucial, as it reinforces how this solution fits into the bigger picture of what we're trying to achieve. So, as we walk through this example, keep in mind how it exemplifies the core ideas we've been exploring. Let's continue exploring the solution. On this slide, I want to emphasize that implementing these strategies is crucial for overcoming the challenges we've discussed earlier. It's about taking a comprehensive approach that addresses both the technical and human aspects of the problem. One key point is that solutions need to be adaptable. What works in one scenario might not be as effective in another, so flexibility is essential. We also need to consider the importance of continuous improvement, regularly reviewing and adjusting our strategies to stay ahead of evolving circumstances. Finally, connecting these ideas back to our overall theme, it's clear that a well-rounded, dynamic approach to the solution not only helps us solve immediate issues, but also sets us up for long-term success. This holistic perspective is what ultimately drives meaningful change. Let's take a closer look at some key properties of the discrete time Fourier transform. First, we have linearity. This means that if we have two signals and their Fourier transforms, the transform of their sum is just the sum of their individual transforms. It's a straightforward yet powerful property that simplifies analysis when dealing with combined signals. Next is periodicity. The DTFT is inherently periodic in the frequency domain, with a period of 2 pi. This periodic nature reflects the fact that discrete time signals are sampled versions of continuous signals, and it's essential to understand how this impacts the analysis of frequency components. Finally, understanding the properties of the DTFT helps us interpret how signals behave in the frequency domain, which is crucial for tasks like filtering, signal reconstruction, and analysis of system responses. Recognizing these properties allows us to leverage the Fourier transform more effectively in our overall signal processing framework. Let's now look at the concepts of conjugation and conjugate symmetry. These are fundamental in understanding how signals behave in the frequency domain. Conjugation involves taking the complex conjugate of a signal, which can reveal symmetries and properties useful in analysis. Conjugate symmetry, on the other hand, refers to the relationship between a signal's Fourier transform and its conjugate. Specifically, that the Fourier transform of a real-valued signal exhibits conjugate symmetry. Moving on, we'll explore time shifting and frequency shifting. These are operations that allow us to modify signals in meaningful ways. Time shifting involves delaying or advancing a signal in the time domain, which translates to a phase shift in the frequency domain. Frequency shifting, on the other hand, involves modulating the signal to shift its spectral content. This is essential in applications like modulation and filtering, where controlling the frequency components of a signal is key. Together, these concepts help us understand how signals can be manipulated and analyzed, linking back to the core theme of how signals behave and transform across different domains. Recognizing these properties enables us to design better systems and interpret signals more effectively. Let's take a closer look at the concept of time reversal. This idea is quite fascinating because it allows us to analyze signals or processes by effectively reversing their time direction. Imagine playing a video backward. This helps us understand the underlying structure or causality in the data. Now, one of the key techniques here is differencing and accumulation. Differencing involves subtracting one data point from the next, which helps us highlight changes and trends over time. It's especially useful for making non-stationary data more stationary, which is essential for many analysis methods. On the other hand, accumulation is about integrating or summing these differences over time. Think of it as building back the original signal from the differences, giving us a smoothed or integrated view. Connecting this to the overall theme, these processes are fundamental in time series analysis because they help us uncover hidden patterns, remove trends, and prepare data for more sophisticated modeling. By understanding how differencing and accumulation relate through the lens of time reversal, we gain powerful tools for better data interpretation and prediction. Let's take a closer look at some important properties related to Fourier transforms. First up is the multiplication property. This tells us that when we multiply two signals in the time domain, their Fourier transform corresponds to the convolution of their individual transforms in the frequency domain. It's a powerful concept because it links multiplication and convolution across domains, helping us analyze systems more effectively. Next is the convolution property. Conversely, when we convolve two signals in the time domain, their Fourier transform becomes the product of their individual Fourier transforms. This symmetry between multiplication and convolution is fundamental in signal processing, especially when dealing with filters and system responses. Then we have Parsevals' relation. This is essentially an energy conservation principle, stating that the total energy of a signal in the time domain is equal to the total energy in the frequency domain. It's a key concept because it allows us to analyze and compare the energy content of signals across domains confidently. Moving on to differentiation in frequency, this property shows how differentiation in the time domain translates to multiplication by a factor of j omega in the frequency domain. This means that taking derivatives in time corresponds to scaling the Fourier transform, which is incredibly useful for solving differential equations and understanding how signals behave under differentiation. Altogether, these properties reinforce the interconnectedness of the time and frequency domains, emphasizing how operations in one domain translate to operations in the other. They're fundamental tools that help us analyze and manipulate signals more efficiently within the broader scope of Fourier analysis. Let's explore the concept of duality. This idea is really about understanding that many systems, phenomena, or ideas have two sides that are interconnected and often opposite. It's like looking at a coin. There's heads and tails, but both are part of the same thing. In our context, duality highlights how different perspectives or elements can coexist and complement each other. Recognizing this duality helps us see the bigger picture and find balance. It also underscores the importance of flexibility in thinking, being able to hold two seemingly contrasting ideas at once. This concept ties directly into our overall theme of understanding complex systems and embracing multiple viewpoints for better decision-making and innovation. Now, let's look at an example to illustrate the solution. This is example 5, which helps us understand how the concepts we've discussed come together in a practical way. As we go through this, I want you to focus on how the key points connect and support the overall theme of the presentation. Remember, the goal here is to see how these solutions can be applied in real-world scenarios, making the ideas more tangible and actionable. So, let's dive into this example and see what insights we can gain from it. Let's look at solution, specifically example 6. Here, I want to emphasize how this example illustrates the key concepts we've been discussing. It provides a practical instance that highlights the effectiveness of the approach. As we go through it, you'll see how the principles we've covered come to life in real-world application. This example ties together the ideas we've explored and demonstrates their relevance and impact. Keep in mind, the goal is to understand not just the theory but how it works in practice, and this example is a perfect illustration of that. Now, let's look at solution. Example 7. Here, I want to highlight how a specific example can illustrate the key points we've been discussing. This example demonstrates the practical application of the concepts, making them more tangible and easier to understand. It's a great way to connect theory to real-world situations. By examining this example, we can see how the solution can be implemented effectively. Remember, the core idea is to use real examples to clarify complex ideas and reinforce the overall message we've been building throughout this presentation. Let's take a moment to look at the appendix. This section is really about providing additional detail and resources that support the main content we've covered. It's a great way to deepen your understanding or explore specific topics more thoroughly. Here, you'll find supplementary data, references, or tools that can enhance your grasp of the material. Remember, while the core presentation delivers the essential messages, the appendix is there for those who want to dive a little deeper. It ties back to our overall theme by offering the extra insights needed for a comprehensive understanding and practical application. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Thank you all for your attention and engagement throughout this presentation. If you'd like to reach out or discuss any of the topics further, here are my contact details. You can email me at contact@Madany.com or Dr. Yasser, Madany@yahoo.com. You can also connect with me through my IEEE email at Madany@IEEE.org. For more resources and information, please visit my website at https://imadany.com. Once again, I truly appreciate your time and interest. Thank you very much.